All right, welcome. Sorry, I just opened the wrong Zoom session to start with, but I think everybody's here now. Oh, we made it to the end of this week. 2, 4, 6, 8, 10, 12, 14, 16, 18. We are shockingly low on attendance today. What's going on? Is there something happening? Yikes. Okay. Announcements are exam 2 is next week in class. Kappa 6, 7 is up as of this morning. You have everything you need to know. You have everything in fact, we're going to be ending fluids today and starting the next unit today. And then the rest of today and Monday and Wednesday, we'll be talking about the next unit that won't be covered on Friday's exam. But the homework will be over fluids that we've already covered and will be on next Friday's exam. I will post by the end of the day an equation sheet for that first exam. And I think that's all I owe you by the end of the week. Any questions? Okay. Then let's just get to it. Right, you might remember we left off last time doing some concept questions on Bernoulli's equations. So let's get right back to those. I have to close this attendance thing down, so please get it in the next 10 seconds if you have not already done it. Okay, closing it down. So we've already seen this particular pipe section. It's going from a small section to a large section, and then changing in elevation, and then increasing in size again. We've already established that the flow rate will be constant through all 4 of those sections, but the velocity will not be the constant through all 4 of those sections. The velocity will be higher where the cross-sectional area is lower, because R is just A times V, and that's a constant all the way through. The final question is, where is the pressure highest? 1, 2, 3, or 4? So I'll just start it. You've got, or are they all the same? You got 5 choices. "30 seconds left. "10 seconds left. All right, 24 people answered this question. I believe there are at least 10 more people than that are enrolled in this class, but oh well. Let's see what the answers are. Ooh, we got some everywhere. We have D being the most favored answer, although not a majority, a plurality, but not a majority. We have A getting some love, C getting some love, and E even getting some love. So let's open up the floor. Who wants to make an argument for 1, 2, 3, 4, or all the same? Isaac. So the pressure has to be highest in 4 because the velocity is the smallest. You're thinking of Bernoulli's equation probably, where P plus 1/2 rho V squared plus rho GY is a constant. So the answer is 4 because the velocity is smallest and therefore the pressure must be highest. Somebody else want to make an argument for something else? Robert? So you're agreeing with Isaac that it's 4, not only because it's moving slower, but because it's lower in height, elevation? Okay. Go ahead.
I guess there's also
the streamlines? Yeah.
Where when the streamlines are close together, that means high velocity and lower pressure. Lower velocity.
That's right. That's not a bad way to do this. We did a visual example where when the streamlines come together, that means high velocity but low pressure, and when they diverge, that means low velocity and high pressure. So that's another argument for 4. The visualization of the streamlines. Not a bad picture to have in your head. There was another hand over here. That's exactly what you're going to say? Excellent. All right, good. Anybody else want to argue 1, 2, 3, or all of the above? All the same. Looks like we have, you've convinced the audience. Let's hope that it's right. So remember Bernoulli. So I think all of these were good ways to think about it, and all of them were right. So let's just think about Bernoulli's equation. P plus 1/2 rho V squared plus rho GY is a constant, is Bernoulli's number. So what does that mean? In some places we're changing velocities, and in other places we're changing Y's. All of those things must also change P, right? And we can see P plus 1/2 rho V squared is a constant. If we change V, we have to change P, and they have to be inversely related. V goes up, P has to go down, as long as we're not changing Y. If Y stays the same, if V goes up, then P has to go down. If V goes down, then P has to go up. So in going from 1 to 2, again, some streamlines are going up and some streamlines are going down, but we can choose the streamline that goes straight through and doesn't change in elevation at all. And remember, Bernoulli's equation is constant along a streamline. So you just choose the right streamline, specifically the one that doesn't change in elevation as it goes from pipe 1 to pipe 2. In that case, the velocity must decrease in going from 1 to 2. The pressure must increase in going from 1 to 2. So 2 has a higher pressure than 1. Now, what about going from 2 to 3? The velocity is now staying the same, but the Y is getting smaller. And if the Y gets smaller, again, the pressure has to go up. We know this should make more intuitive sense to you. The further down you go in the well, in the pipe, the higher the pressure has to be. All other things being equal. And in this case, they are. The velocity will be the same because the area isn't changing as you go down. So 3 should be greater than 2, should be greater than 1, and 4 should be greater still because, again, we're not changing Y this time. We're just changing V to an even slower velocity until the pressure must go up again. Here's a challenger question that I'm not going to ask specifically on the slide, but will be important for homework next week to think about. If you were to have a vertical pipe moving up out of 3, let me actually draw this. This is actually a thing. Let's say you had the same thing. You've got a pipe. Let's not worry about it changing size now. So it's the same size always. But let's say you've got a vertical section of this coming up. And let's say there's water going all the way up to some other point up there, but it's closed at some level. You're not allowing the pressure to vary much at all. What is the pressure here and here at the same height? In other words, maybe I'll think about this slightly differently. It was a well-formed question, but I don't think I was good enough at explaining it. And I'm not sure it really asked what I was wanting to ask. So let me see if I can reformulate this on the fly with very little sleep last night in a way that will make sense. Let me ask it more specifically exactly how it's going to be asked in the homework this week. I can't remember if it goes from small to large or large to small. It doesn't really matter. Let's go from large to small to large. And let's, again, so water's rushing through here at some rate, right? And let's have now some open tubes coming up in both directions. This is actually called these open tubes, so they're open to the air. So water can be pushed up into them, and it will be by the pressure below it. The question is, in which two of these pipes will the water be highest, one or two? Or will it be the same? Go ahead, Bailey.
Going from like the thinner section to the thicker section, like the thicker section, the pressure would be higher. So it would push it further up.
So you think since the pressure is higher in this part of the tube here than it is in this part of the tube here, that the water would be higher in tube 2 than it would be in tube 1. Nobody else who had raised their hands is raising their hand again, so they must all agree with you. That's exactly right. This is actually called a flow meter. You can actually do this. If you can't probe directly the flow of water down below, you can actually tell the difference in flow between two sections of a pipe just by one of these, the difference in height that the water is above each of those sections of the pipe. Even though that water that's in the pipe is not moving at all, it is affected by the pressure of the water that's below it supporting it. And you can actually determine the difference in flow rate from one power pipe to another simply by attaching these vertical, they're called flow meters, to the top. And you'll have a question about that for this week's homework, where you think about how the difference in height will relate to a difference in pressure and how you can relate that to velocity flows with Bernoulli. It's going to be a glorious problem. Enjoy it. It's going to be great. You're going to love it. Okay. So that's the concept question with Bernoulli. The only really other thing we have to do with fluids is to wrap up the challenge problem that I gave you last time. Did anybody have a chance to solve it? Does anybody have a plot or a graph for me? I've actually seen one of them from Isaac. Anybody else have a chance to plot it? If you remember, the challenge problem was we did a water clock and we solved for the flow rate out the bottom. And we found that if the area on top is much, much bigger than the area in the bottom, then as long as the H isn't moving too fast, that the flow rate should be fairly constant. But it won't be completely constant because as H changes, that will be changing. So the question was, can you come up with a function of area as a function of a formula for area as a function of height that will make it so that that value of the flow rate will be constant even when there isn't a value of H, even when there isn't, even when H is changing rather dramatically or at all. So if you're interested, you can solve this analytically. Radius as a function of y looks something like this. You've got r naught, you've got 1 over 1 minus 2gy over vb, which is the velocity at the bottom, to the 1/4 power. That's what it looks like analytically. What does it look like in practice? It looks, I was impressed that some were able to even qualitatively think about what this would look like, because it does have to taper as it goes in, but it tapers extremely dramatically. And in fact, this equation is only valid for this is positive, right? If this goes negative, then you get inverse, then you're trying to take the quartic root of a negative number, and that just doesn't work. So this only works for 1 minus 2gy over vb squared greater than 0. And you can solve this for y. This is y must be less than vb over 2g. This sets a vertical limit to how big this thing can be. You cannot build it any bigger than this or it won't work. What does it look like? It looks something like this. Actually, I've drawn it much better on the right than I have on the left. It starts off extremely shallow, and then it takes a deep dive in the middle, interestingly. So this isn't going to be a very practical water clock. It's going to drain almost instantly, but while it's draining, that flow rate will be constant even as the height goes down. So that's exciting. Okay. That is the end of our fluid section. Did it in 20 minutes. Nice. And it's also the end of what we're going to be talking about for the exam next Friday. So all of this, unlike last time when we had an exam and we didn't have a homework set the next week, this time we're going to have 2.5 classes of material on the next topic. So I will be posting a Kappa set next Friday that will be due next Thursday that will be over this material that we're covering right now. So we're not going to have a week off of homework this time around, just so you know. Thermal physics. I know, it's going to be exciting. We're going to start with chapter 18, although I think there's more than one of them that we're going to get to before we're all done with this unit. So you have some intuition for this going in. It is a rather large part of our daily existence. Our bodies naturally regulate to the same temperature all the time. Our bodies are tuned to a specific value. We are sensitive to changes in the in the environmental temperature around us. But what is temperature? What does it mean to say that something has a specific temperature? How do we quantify it? We're not going to answer that question now. You may already know the answer to that question at some level, but we're going to think deeply about what temperature means, because it isn't even necessarily obvious that temperature should be a thing. So we're going to first lay down some groundwork on what temperature is and why it might not be a thing and why it is a thing, and some warnings Basically, this is going to be a continuation at some level of our fluids discussion, although now we're going to be talking about fluids that are compressible. We're not going to be thinking about how they move from place to place, but we are going to be thinking about what happens when you squeeze. We're going to be thinking about gases now, really. And we're going to be thinking about what happens when you squeeze gases together, because gases are quite compressible, and thinking about what happens when you let gases expand and do work and things like that. So, so we're still thinking about fluids. But now we're thinking about compressible fluids. Which are almost always gases. Okay. So we are interested in things that I'm going to call state variables. Specifically, the state variables of a system. What do I mean by state variables? I mean those variables that describe the substance itself. Can you give me some examples? Anybody can give me an example of a state variable? Density, yes, excellent, absolutely. Pressure, yes. Potential energy, yeah, sure. There's a lot of ways that potential energy could be stored, some of which are state variables and some of which aren't state variables. But potential energy certainly can be a state variable. Temperature, sure. Can anybody think of a variable, temperature, that would not be a state variable? Actually, pretty much anything you can think of that would describe a substance would be a state variable. We break them up into two different kinds of variables, though, and some of them are more interested in than others. So let's think about intensive state variables and extensive state variables. So intensive are the property of a property of a substance, not the quantity. So they are independent of quantity of the stuff you have. That says quantity. I'm sorry, you can't read it. So for instance, mass is a state variable of, let's say I've got this cookie. Mass, the mass of this cookie is a state variable, but the mass is not an intensive variable because it depends on the amount of cookie that I have, how much mass it has. Density, though, is a good state variable because it describes the cookie matter that makes it up rather than the amount of the cookie that I happen to have in my hand. So temperature, density, pressure, basically the variables that we were interested in our fluids discussion, plus temperature. Extensive, we're not going to be as interested in, but they're still important. Properties that change if I were to take a second cookie and smash it into that first cookie, the density wouldn't change, the pressure wouldn't change unless I smash it really hard. Or if I just made a big cookie that were twice as big, but these variables would double when I double the amount of cookie matter that's there, right? So these are the properties that change if you add more stuff. So volume, mass, energy, number of particles, those all will go up as you add more cookie dough to your, or cooked baked cookie to your substance. Okay, we're generally going to be thinking about closed systems. Some simplifications, the caveats before we get. We're at least showing you the details that we're shoving under the rug as we shove them under the rug. You're welcome. So we're going to talk about closed systems, meaning N and mass are constant. Things like N and mass are constant. So we're not going to be adding another cookie to our systems very often. And we're going to be concerned most with just 3 state variables. And those are temperature, or density, temperature, and volume. 2 of these are intrinsic, and 1 of these is an extrinsic property. These are not independent. In general, if you change the temperature, you cannot leave both the volume and the density constant. You have to change one of those 2 at least. Often you will have to change both of them. Okay. Also, if you specify 2 of these state variables, you will often get the 3rd. Okay. So let's talk about these things. We already have a good handle on what temperature, on what volume is. Actually, I think this is pressure. I have density in my notes, but I'm pretty sure this is pressure, not density. That's much more what I'm interested in. Exactly, PV equals NR. This is, we're definitely thinking about pressure here and not density. So my bad. It's not. I can't even blame my tiredness on that. That's just wrong in my notes. Okay. Pressure. That's P, not a density. Okay, great. So 2 of these things we already have a pretty good handle on. Volume, I don't really have to explain very much. We know what volume is. It's some cubic dimension of space. Pressure, we've just spent 2 weeks talking about what pressure is and how it's defined and how we can calculate it and how it works. So hopefully we understand what pressure is. But temperature is the last thing that we might be interested in having some clue about what's going on. So let's think more carefully about temperature. P and V, we've already covered. Let's think about temperature and what it means to have temperature. So we're going to begin with writing down the 0th law of thermodynamics. I know. Why would there be a 0th law of thermodynamics? Well, the reason you have a 0th law of thermodynamics is because this was actually discovered in the 1930s, really, really late. And there were already a 1st law of thermodynamics and a 2nd law of thermodynamics and I don't know, maybe even 3rd and 4th and 5th law of thermodynamics. But they realized that there was something important that they had been assuming for all these other laws of thermodynamics to be true that they hadn't actually written down as a law. And you can't just change the law number of a law willy-nilly, right? So instead of slotting this in at 1 and moving all the other ones down 1, they slid this one in at 0. I suppose the natural question is, if we find something more fundamental than this and have to put it above that, will that be the -1st law of thermodynamics? Probably, I don't know. Hopefully we won't ever come to that. But that's where we're at. So that's basically the history, why it's called the zeroth law of thermodynamics. And interestingly, it came along rather late. People didn't start really writing this down until the 1930s. Okay, so here's what the zeroth law of thermodynamics says. I'll write it down, I'll say it, and then we'll try to understand what it means. If two objects any two objects, a cookie and a table, a person and a table, a person and a cookie, a mouth and a cookie, whatever, anything. A and T we're going to I'll talk about why we're going to call them A and T in a second, are in thermal equilibrium. What do I mean by thermal equilibrium? I mean that if I take these two objects and isolate them from the rest of the universe and put them in contact with one another, there is no net energy flow from one to the other or the other to the one. That's what we mean by thermal equilibrium. Put in contact, I'll take away, this isn't really a dash. Put in contact, what I mean by thermal equilibrium, I mean put in contact and no net energy exchange occurs. So what would be an example of this? Why did I call it A and T? Well, let's say T is a thermometer and A is some substance, say a bath of water or something. And I put my thermometer in A and there's no net heat exchange between the thermometer and that substance. Question? Right, we're going to get to temperatures. We haven't yet defined what a temperature is yet. All we're saying with thermal equilibrium is, so if I'm at thermal equilibrium with this table and I touch it, there's no net energy transferred from me to the table or from the table to me. I can tell you that's not the case right now because it feels kind of cold to my hands. There is some energy being transferred from my hands to the table as we talk. But if there weren't, then I could say I am at thermal equilibrium with this table. That's what I mean. Okay? You're right to bring it back to temperature, but we haven't gotten there yet. So they didn't even have to start at thermal equilibrium. If eventually they come to thermal equilibrium, right? Put that thermometer in the bath and wait a while, eventually they will come to thermal equilibrium if they're isolated from the rest of the universe. And then you can say this thermometer and this water bath is at the same, are in thermal equilibrium. Okay, if you say that, and also B and T are in equilibrium, so in other words, you remove your thermometer from bath A and you move it over and you put it in some other substance B, and there's still no net exchange between that thermometer and that substance. Then A and B must also be in thermal equilibrium. Exactly. So you can put those two water baths or whatever substances they are together, they don't even have to be water, and they will not exchange, there will be no net energy exchange between them either. Okay? This may seem obvious, which is why it took until the 1930s to actually write this down and realize that it was kind of important. But if there weren't such a thing as temperature, this wouldn't necessarily be the case. If, for instance, how the thermal properties of something depended on the material of which it was made. It's possible for this to be in, it might be possible for this to be in thermal equilibrium with this and this, but not to have these two things in thermal equilibrium with each other. But there is something, this is basically saying that there is such a thing as temperature and that it's a useful way to quantify things about other things. That is a useful independent of what the thing is made of, we can define a temperature of that thing and have it be a useful quantitative thing to do. Thermometers work. That's basically what this says. Okay, so this leads to the fact that temperature is a quantifiable, measurable quantity. Temperature is a quantifiable, measurable quantity. Which is useful. Okay, how do we do it? So let's talk a little bit about temperature scales because they're weird. And there's a lot of them. Originally, every temperature scale that was ever made was a 2-point scale. You had to define 2 points in the scale in order to define the scale itself. Originally, all are 2-point scales. So, for instance, Fahrenheit. Familiar with it? It's what we grow up learning about and dealing with in our everyday lives. This Fahrenheit scale was invented in 1724. And I'm not even sure it was Mr. Fahrenheit who did it. I think he just quantified it or made the actual thermometers. I can't even remember. I watched this video like 2 years ago, and it's really interesting. The history of Fahrenheit and Celsius and all these scales is actually really fascinating. So what are the 2 points of the Fahrenheit scale? Does anybody know? It is not. We define it now to be 0 is 32, freezing is 32, and boiling is 12. Those were not the original 2 points that were used as the scale markers. Let me know what the original 2 Fahrenheit markers were. It's actually 0 and 100. Sorry? It's not alcohol, but you're on the right track. It's some other substance that on the low end can get much lower than freezing. It was not pickle brine necessarily, but sea brine. It's like salt water, like really briny water. You're right. It is the freezing point of really, really salty water, really, really salty briny water. Basically, so they could measure where that transition happened, and they could define that. It was the coldest thing where they could really measure in the 1700s, where they could really measure something was actually physically changing. A set thing happened at that particular temperature for this very, very briny. So set the 0 points. The first one, 0, was set to be briny water with ice mixture. And you can have a water-ice mixture in thermal equilibrium that isn't actually moving towards more frozen or more. We'll talk about that in a bit. I mean, what the second one was. I'll give you a hint. It's 100. It's not the boiling point of briny water. That's a good guess. The boiling point of regular water is like 212, right? So this is way below that. What's about 100? What's body temperature? It's basically body temperature. Although apparently we're 98.6, right? Apparently they used horses instead of people. And I guess, I don't know if there's any horse experts in the audience, in the class, but apparently horse body temperatures are slightly higher than human body temperatures. So they got to, so human body temperatures are therefore defined. So 100 is basically body temperature of a horse. And so humans come out just a little bit, therefore below 100. Today, it's not defined by that because you'd have to specify exactly how briny it was, and you have to specify which horse you're talking about, whose body temperature is exactly. It's not a very convenient way to measure, to set your temperature scales. It was convenient in the 1700s. It's not really convenient anymore. So today, it's still a 2-point scale, but as you pointed out, Bailey, today it's the freezing point of non-briny water. Of pure water equals 32. And I'm going to actually put the degrees Fahrenheit. Degrees Fahrenheit. Oh, dang, missed it. Degrees Fahrenheit. And the boiling point of pure water is 212 degrees Fahrenheit. Obviously, the F stands for Fahrenheit. Why do we need the degrees? Well, let's yes. Why do we need that degrees there? You'll always see it both for this scale and for the Celsius scale. Oh, so to distinguish between other things that might be capital F. Good guess, but that's not actually it. There's a reason why that degree has to be there, and it's not there for some other things that also have some overlap with other terms.
Is it because it's not absolute?
Yes, the Zoom. Who was that?
It was Noah.
Well done, Noah. It is because it's not an absolute scale. In other words, 0 is not the true 0 temperature point. It is a scale whose 0 point is offset from the true 0 point. It would be so, and so you can't just plug this into a formula for temperature and expect it to work because it will not. You have to use an absolute temperature scale in order to use that. It's sort of like if you were to choose a meter scale or a length scale where 0 was not actually 0. It was some non-zero length, right? You wouldn't be able to just plug that into, you would be talking about some degree length thing because it did not actually go to 0 at length equals 0. You would never do that for length, but we do that for temperature because we didn't even know that there was a 0 point for temperature scale when we set these things up. It turns out that there is, and that's pretty cool. We haven't gotten there yet. How much time do I have? 5 minutes. Okay, we can do this. Okay, you can go over here. Okay. The other one, so note the degrees. It's needed because it's not an absolute scale. Right, so again, if you double the temperature, say if you go from 20 degrees Fahrenheit to 40 degrees Fahrenheit, you have nowhere near doubled the actual temperature of that substance, right? So you have to be you have to be careful. It's not a true scale of temperature. Okay, Celsius. That's the other one that is in common use these days. Interestingly, you might think this came along way later when people were more sophisticated about these things. It was invented 18 years after the Fahrenheit scale in 1742. And it defines its first and second. Again, it's going to define them at 0 and 100, but those are, as you probably know, the freezing and boiling points of water. These also need degrees Celsius, because this is also not an absolute scale. So 1 degree Celsius is 1/100th of the way between the freezing point and the boiling point of water. Okay, about 100 years later, it was discovered that (1846 or so), it is discovered that there was an actual 0 point, a true 0 point for the temperature scale. There is a temperature below which you cannot cool anything else beyond. And we call this thing absolute zero. Cannot go colder. T cannot go below absolute zero. And so we can now define a scale that is a 1-point scale. Now that we know what our 0 point is, most scales you only need a single thing that tells you how much you're stretched in numbers. Now that we have defined the 0 point, we can define a 1-point scale, which is done, and the Kelvin scale is what we're going to use for that. A 1-point scale. I guess you could, 0 is 0, and that's what we're finding as our base. So 0K is absolute 0. How is this defined? We don't need the degrees anymore. You can say 0 kelvins. You can say 10 kelvins. You can say 150 kelvins. And if you double the number of kelvins, you have actually doubled the number of, doubled the temperature of that object. So you can say kelvins. You can't say Fahrenheits or Celsiuses because it's not really a thing. So, and this is defined such that delta 100K is still the interval between the freezing and the boiling point of water. So it takes the Celsius scale and maps it down so that 0 is on 0. The formal definition of this, actually, this is the rough definition. This is how it was come up with. What is the formal definition is that 0 is 0, and the triple point of water is 273.16 Kelvin. We'll talk about what triple point is next week. Okay. Have a good weekend.